Okay, so as I said, I'll continue a little bit with the theory first, and then we'll see where we are in half an hour. And I think I'll just do the one exercise for this tutorial then, because the further we are along, the more exercises there is to do. Okay. So where we ended this morning is that we wrote down this definition for the geometric entropy or entanglement entropy associated with an interval A in a two-dimensional CFT, by which I mean 1 + 1 dimensional. And so this is the definition we'll use to calculate this geometric entropy. And so the strategy for calculating the entropy according to this definition, following this definition, is the following. So first, apologies. First, we want to make sense of this object here, this z of n, what it is. And then once we have that object, we can plug it in this formula, okay? So step one is, what is z of n? And the statement is that we can make sense of this object, which is defined as a trace of the nth power of the reduced density matrix for positive integer n. So for positive integer n, we can make sense of this object as giving you an n times replicated system. In fact, there will be two different ways in which we can interpret z of n as an n-fold replicated version of your system. And we'll discuss that in detail. But let me just write in words. So we can make sense of this object for n, a positive integer, in which case z of n gives us an n-fold replicated description of our system. So the strategy for finding this geometric entropy will be the following. We construct this z of n for positive integer n, in which we understand how to make sense of it. Then we plug that object in this definition, and according to this definition, we'll then have to take derivatives with respect to n and a limit of n to 1. And so for those two steps, we'll have to analytically continue our obtained z of n beyond n integer. Okay. So this whole strategy that I mentioned is called the replica method. Okay, so let's start with that. But to start with that, I'll repeat some of the notation, the pictorial notation for density matrices of this morning. So you have it on the board, and we can readily apply it to what we need to apply it. So what we wrote is that the density matrix pictorially is something like this. And it's a matrix that has matrix elements phi prime, which you get from putting a phi prime here and a phi here. Good. And so another notation for this phi prime matrix element is the phi primed entry of rho. Okay. Well, let's use this space also. And we had that the trace of rho is obtained from putting the same boundary conditions phi and phi here and integrating over that phi, which amounts to gluing your path integral along that line into just this. Okay. Okay, I'm reminding you of this so that you would follow what it means to write down the trace of the reduced density matrix. Okay. Remember, A is defined as some interval at this constant time slice t is 0. So let me just write it and see if you understand. So sorry, the trace, sorry, I thought something was going wrong. So the reduced density matrix is defined as tracing the degrees of freedom in A bar out of the density matrix. Okay, the density matrix we have here. And A is this interval that we chose at the constant time slice, and A bar is all the rest. Okay, so what this is telling us is that we need to trace the row, meaning gluing those boundaries here together, but only in the region A bar, and leaving out A. Because you're not tracing, so row A is defined as tracing not over everything, but only over the degrees of freedom in A bar of row. So then what you have left then is this object in pictorial notation, which is a path integration from minus infinity to infinity, but there's a slit left open here along A. And this is where you still have two open slots to your matrix, row A, where it can take on boundary conditions. Okay, that's clear, or? So let me write down the matrix elements of row A in the same way that here I wrote down the matrix elements for the full density matrix. Okay, so row A can take on a field configuration phi prime here at 0 plus, but only for x in A. Okay, that's only where there's a slot left. So this is why now I'm explicitly writing here that these field configurations depend on x. I could have done this here also, but I just didn't bother because it's valid for all x, right? So here I could have put x, meaning all x from minus infinity to infinity. So here I need to specify that the matrix elements are for x in A. And okay, so they are given pictorially by changing your dashed lines into solid lines corresponding to choosing a phi prime on this side and a phi on this side. And so in formula notation, you would have the path integral with the following boundary conditions. that the top slit is fixed to be, well, the field configuration at the top slit is fixed to be phi prime, and the one on the lower side of 0 is fixed to be phi. Okay, since I chose phi as a boundary field condition, let me change the dummies to phi hat. Okay. So this is in formula form what the matrix elements of row A are. And now what we need to do, so remember what we're trying to do is construct this Z of n, which is a trace of the nth power of row A. So let's start with just taking 2 powers of row A and understanding what that is. So I'm going to take row A and square it. Okay. So what is this? Row A is a matrix. Squaring a matrix, I just need to use matrix multiplication. Matrix multiplication, you will write using the components of your matrix. Okay, so because I'm going to first write this in terms of matrix multiplication, let me write it in components first. We have that the phi prime component of rho squared phi tilde, phi prime, is this object. Okay, this is nothing else than saying that the ijth matrix element is the of the squared matrix is the I kth times the k jth. Okay, and you're summing over k, which is here your dummy phi tilde. Okay, so this is just simple matrix multiplication. Let me write it. So here we're just doing matrix multiplication with a dummy phi tilde. Okay, that's the field that we're integrating over. But let me now write this in pictorial notation, okay? So I have 2 times this picture that I have here. Remember, this I can write as the phi prime element of rho A. Okay, so I have 2 times that picture. 1, 2. Here I have the phi tilde element. Here I have the phi tilde phi prime element. Okay. And now I need to integrate over the dummy phi tilde. So you see that what I'm doing is again this gluing operation. I'm filling in the boundary conditions here and here. I'm imposing those field configurations to be identical, phi tilde and phi tilde, and then I'm integrating over all possible such phi tildes. So this is again this gluing operation. And okay. The best I can do on the board is use a color to tell you that this top line and this bottom line are connected. They are the same. You're gluing this copy to this copy along that line. Okay? Okay, I'll write one more pictorial representation. Let me first add the phi and the phi prime, which I still have sitting here. Okay. And so one more way to write this is to write my copies flat. So this is my first copy. I have a phi downstairs, a phi tilde upstairs, which is identified with the phi tilde on the next copy. So, I don't know. This notation, you just have to remember what is meant by it. And then here a phi prime. It's clear what this is. What this is showing. Right. Then let me go to the next board. Well, so what I'm writing here is immediately the matrix elements, just because it's most clear in that way that I'm just doing a simple matrix multiplication. But if I just want to write the actual matrix, all I do is unsolidify the phi and phi prime lines back to dashed lines. Then I again have a matrix that can take on a value phi and a phi prime. Okay? So the rho A squared is this, or is, no, sorry, dashed on the bottom. Dashed on the top, okay. Let me add the identification again, as such and as such. Okay, so this is what rho E squared is. Any questions about this? So, very good. So if you understand what rho A is, and why it has this pictorial representation of where you path integrate, then you'll understand immediately the following picture for the nth power of rho A, which is just the same picture, but with n copies. So I'm going to immediately write this code. This one. This one. So I have copy number 1, which is glued along this slit to the next copy. This one is glued along the next, along this next slit to the next copy, etc., etc. This one is glued to the previous one. That's it. This is the nth power of the reduced density matrix. Next, let's take the trace. Okay, so taking the trace of this object means imposing boundary conditions on the remaining dashed lines, identifying those boundary conditions, integrating over them, which amounts to gluing them, which is taking this line and this line, solidifying them, and identifying them. Okay? So this is a trace of the nth power of the reduced density matrix, and this is the object that we called Z of n. So we've now succeeded in constructing this object Z of n. Okay? So let me write it in formula form. In formula form, we have basically the path integral over this complicated geometric structure. Okay, so my coordinates, it's a bit hard to draw the coordinates. So before, we just had x going this way and t going this way. So we still have x and te going this way. But these are now coordinates that span this whole thing. So that move to different sheets in this geometry. So this is more clear in the formula form, which is you take the path integral. Oh, sorry, what's happening here? Phi of x and te. Okay. So in the action, we integrate x and te over this whole manifold, which we call the replica manifold with a curly r. You need to specify how many copies, n, and you need to specify where the slit is, which is along A. So this geometry we call the replica manifold. It has to be labeled by both those parameters, both those things, n and A. Okay. And so here, again, this is just path integral notation for integrating over all the fields on this manifold. So what we've introduced here is the replica manifold, which we write as curly n comma A. And it's just basically this picture is the replica manifold. All right. So the replica manifold is a replicated world sheet. By world sheet, I mean the geometry that x and te, your coordinates, span. Okay, so it's a replicated world sheet. It's an unsheeted surface with the following characteristics. Namely that if you're moving around the edge of A, it will take you 2 pi n angles to arrive back in the same point. Because every time you take a circle, you will end up first on a higher sheet. And you have to go through n of them before you're back in the same point. So the characteristic, but I'll do this a bit more in detail. But the characteristic is that it takes you 2 pi n to go around the boundary of A, which I write as dA like this. Okay, so the boundary of A is just those two endpoints, x1 and x2 of your interval. So dA is just those 2 points, x1 and x2. So the fact that it takes you 2 pi n to go around this, the boundary of A means that there are branch points at those locations and also conical singularities at those locations. Namely, there's conical excess because instead of going around once, you go around n times. Both of those statements about the branch points and the conical singularities, I'll give a bit more details just now, okay? But I'll do it on the next board, yeah. Well, okay, well, no, I decided I'll do it on that board because I want to actually work with the picture of the replica manifold. But what I'll do is I'll get rid of this. Okay. Okay, so the question is, where will you travel on this sheet if you are living in this geometry? And so just follow with me. If you start somewhere here, I'll write the conclusion, but just follow me first. So if you start here, and you rotate around the point x2, which is this point. Remember, actually, these two lines are infinitesimally close. It's 0 plus and 0 minus. Okay, so I'm rotating around the right endpoint of my interval A in the counterclockwise direction, okay. So I arrive here. Once I arrive here, I have to jump to this location on this sheet. I keep rotating. I have to jump again when I get here. So this happens n-1 times until I get here, until I get here, until I get back here. Okay? So this is a statement that if this is point x2, that I have to go 2 pi n times around it to end up back in the same point where I started. If I start somewhere in the middle, let's say here, and I rotate it, so I start now here, I rotate again in the counterclockwise direction until I hit this spot. Then I have to jump to here. Okay, I was rotating in the counterclockwise direction, so I jump here, I keep rotating in the counterclockwise direction until I come back here, which means I jump back in the other direction, back to this point. So this circle is only 2 pi. Did you follow? Okay, so the circle in the middle, if x1 is somewhere here, the circle in the middle is still just 2 pi. Obviously, a circle anywhere here will be 2 pi. And nothing special is happening on that location of the sheet. So here we also have 2 pi's, okay. Then the remaining one is x1. For that one, I'll go in the clockwise direction. So again, I start here, close to the x1 point. I rotate in the x1 direction until I hit this point. Then I have to jump here. Jump, 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 jump. Jump back. So this is 2 pi n that it takes me in the clockwise direction going up. So going up in this direction, going up. So you're going up to the next sheet by moving counterclockwise around x2 and by moving clockwise around x1. Okay? Right. So these are the characteristics of this manifold. And you can think of this as having branch points at those two special locations, x1 and x2. So here's x1, has a branch point with some branch line. You go up by going counterclockwise around this point, so you go up in this direction. This is going up to the next. Go up means to the next sheet. And then you have a second branch point in x2. It also has its branch line. But here, you go up in the other direction. So this is now going up. Or said otherwise, if I move in this direction, I go down. So this means that the effect of these two branch lines cancels in this region. Because if I move in this direction, I'll go up first, going through this branch line, but then I go down immediately again through this branch line. Okay? So this is why in the outside region you just turn circles of 2 pi. Right, in the inside region you actually do go up but then back down again. So that picture of what is happening in your manifold you can think of as having branch points at x1 and x2. That's just a point to make here. And then I also said that means that there's conical singularities at x1 and x2. So at dA, the boundary of A. So this is, of course, precisely because of this point, because it takes you an angle of 2 pi n to go around. So a conical singularity, I don't know if you've encountered it, but this is what happens when, so let's say you have a disk solution, so a disk manifold, I mean. This is a flat geometry if the polar angle is 2 pi. Okay, so if you would write down the metric for this thing, then it's a non-singular metric. So if you write down the metric in polar coordinates, it's a non-singular metric only if theta, your polar angle, is identified with theta plus 2 pi. Now, if for some reason you want to think of a metric that has a different identification of the angle, you would have, so let's say you want to identify theta with theta plus some factor of 2 pi which is smaller than 2 pi. So 2 pi over 2, for example, then what you would be imposing is that you close this disk before you're completely moved around the origin. So if you do this, you'll see that what happens is that you make a cone. Okay? And so as a result, your origin in polar coordinates of the disk will have a conical singularity at this point, meaning it has a divergent curvature there. Okay? This is the main example of a conical singularity, and it's of course easiest to think of a conical deficit like you have here in the situation of the cone. So where you try to, or where you identify your angle before you reach 2 pi. Here we have the opposite, where we're identifying, so we have a geometry which would be nice and flat if it was just one copy, where everything just takes 2 pi angles to go around any point. Now we have a geometry where there's 2 special points where you have to go around 2 pi n times. So what that does is that it creates conical singularities at those 2 special points, which do not have a conical deficit like in this simple case, but a conical excess, which is more difficult to think about, but it's really the same thing, okay? Really the same thing in the sense that it's also a conical singularity. Okay, so we have conical singularities with conical excess because you're identifying your angles with the too large angle, okay, at dA. Right. This is where I was going to stop, and then I can give you the exercise that I had in mind. You can do this here. So let's go to rechts. Okay. Any questions before I go to the exercise? So let me write down a few equivalent expressions for the geometric entropy. Question, yeah?
So with this nice picture, you have not actually analytically continued in n, right? We're
No,
still
that's
in
right,
integer
yes.
n. So is non-integer n then some kind of continuous branch covering, or what is the geometry corresponding to that?
Well, the geometry is very hard to think about in
Right.
this picture.
But it's still going from, like, for example, if you, I don't know, have something like, you also have like continuous coverings of like usual manifolds, right? Just you don't have branchings where you have, instead of a double covering, like an infinite covering. Is this a similar picture here then?
Well, not really, because you want to make sense, for example, of the value n equals 1 minus epsilon, or 1 plus epsilon. So that doesn't really work in this picture because you want a certain number of copies, meaning n to be positive integer. There's a way in which to make sense of the replica manifold for continuous n, and we'll get there in a later lecture. If you follow through with this derivation with this replica manifold before doing any conformal map that can help you out with this question, what you have to do is actually write down z of n and then analytically continue that expression. And there's an argument for why the same expression also holds for complex n. But again, this is something that we'll see next time probably, yes, yeah. Right, so there's an object called Renyi entropies, which I didn't introduce in the lecture, but I'll introduce it now. So it's an entropy associated with this interval A, which is still labeled by the number n. And the entanglement entropy that we've been talking about is really the n-to-1 limit of this Renyi entropy. So the Renyi entropy is the more difficult object. And the Renyi entropy is defined as follows, as the log of the trace of the reduced density matrix to the power n over 1 minus n. Okay, and you have to, for getting the entanglement, you have to take the limit n to 1. So there's 3 expressions for the entanglement that you can find starting from this definition. And so 2 of them we've already written down in the lecture. The third one is this one, which you can see as a intermediate result for getting to the second equivalent expression, which is the von Neumann entropy definition. And the third possible expression is this one, which we're using now for our replica method derivation of the entanglement. So here are your 3 equivalent expressions, and the task for you is to understand, to derive why all these expressions are in fact equivalent. So the starting point would be this. And I would say first you move through this, then to this. And then separately from here to here is actually the simple one, okay? This you can almost see immediately from what we called z of n. So there you go, you have 15 minutes left.
Sorry.
Yeah.
The first
Yes, so most of the time people would write this as the limit of n to 1, like this.
That's understandable.
Ah, okay.
In the exercise, the first one, derivative of trace rho. That means there is no n. Either you say n.
Wait, log trace. Let me check my expressions. They're correct. Now back to your question, sorry.
Yeah, so I don't understand the first one. Its derivative with respect to n of trace is correct.
Yes.
But other expressions do not contain n. You either put n equal to 1 at the end, or for example, the second one does not contain n.
Sorry. So all of them still have n to 1. Yeah. So this is what you mean. Yeah. Yeah. Sorry. Yeah. Sorry, I forgot it in this expression. That's right. No, sorry. Yeah, sorry. No, it's the end of the day for Niels. Okay, sorry. Another mistake on the board, so the bracket was in the wrong place in the last expression. Thank you for that. Just to comment, I added one line here to this discussion of the branch points and the branch lines, which I said in words, but I didn't actually write down this last bit, which is that because they cancel here, effectively you have this type of picture. Yeah. Yeah.
Can you talk a little bit about when the replica trip is but not well defined and when is it well defined?
You mean in terms of this analytic continuation? Well, so next time I'll discuss this general argument for why the analytic continuation works in this replica manifold derivation. It's the argument that's in the review, but then later on, when we discuss a replica manifold that does make sense for continuous n, that by itself is an argument for why this analytic continuation in other derivations has to be well defined, because there's a pathway that can make sense of the continuous replica manifold. So that's the way I think of it, but this mathematical way I'll mention, but maybe not in too much detail. It's this paper by, you know what I'm referring to? Is it Versailles or?
I mean, I know that Zimbabwe has a review different.
No, it's not that, but that would be useful. But it's sorry.
There's a review paper, there's some Japanese guy on the replica trip and all the entanglement and CFT that comes up.
Okay.
2013, I will check it.
Is it in
Yeah, let me check. It's Sulu Duken, I think. Yeah, I just mean here in the review, there's this paragraph, which is all I write about the analytic continuation, and I refer to 8, which is Sulu Duken, I think. Let's see. Yeah. So there's a page there that explains this in more detail.
struggling to know where to start here
Yeah.
because how, I guess in these expressions implicitly you're thinking about n as a continuous variable, like even the differentiable variable, but then I don't know what this object rho hat to the power n is.
Yeah, so the place to start, so the first thing to do would be from here to here, which is a simpler one,
Okay.
because Zn is defined somewhere on the board, probably
That's
so.
what this is, right? That's
The trace of that
yeah.
thing, yeah. So from here to here, try that one first. And then from here to here, there's a derivative appearing.
Mm-hmm.
And the reason for that is because you're using a limit rule, a famous limit rule. Because if you actually try to put n
right, I see.
equal, yeah.
Yeah. Okay. Thank you.
So it's 2 to 6. I wasn't planning because there wasn't too much time to actually go over the solution, but we can if you want in the next exercise session. Just let me know if you're struggling, if you're stuck. I can give you the general advice or tip that I just said, but maybe you heard on the mic. Would that help? So, and we can end there then. So, as I said, the simplest one is going from here to the third expression, because you know what Zn is, namely this thing up to the normalization. So that you have to take into account, okay? So here to here is what you can do first, and then the second advice would be from going from this expression to this one. You see that there's a derivative appearing. The reason that appears is because you're using a famous limit rule that you need if you actually try to set n equal to 1 in this expression. Okay. And then once you're here, from here, you go from here to here. Let's see if that helps. Let me know next session if you want to come back to it. Yeah. Yeah. The last statement. So the statement being going from this expression to this expression. And then the next one, there wasn't much of a statement at all, just that once you have this, you can work it out further to this. Okay, but I think we should wrap up here. Well, I'm looking at the organizers.
Then thank you very much for this exercise session and the continuation.